Good morning, everyone. Welcome back from your bank holiday breaks. Hope you all managed to get some rest and relaxation. And today we are starting module 2 of the HSMA program. So after our initial intro module where we looked at primarily coding in Python, but also some other concepts around introducing the modeling process and data science. We're now, for the rest of the training, basically going to be delving into various areas, starting today with discrete event simulation for pathway and queuing problems. And I mentioned this at the start of the course, but I'll reiterate it again now. We are not expecting any of you to become experts at everything. There's a reason why I don't teach everything on this course. I'm no good with web apps. Sammy's much better at that kind of thing. I don't do geographic modeling. Sammy does all that. You aren't. We're going to show you so much in terms of what we do as a team. There's no way that you will become an expert in everything. So there will be some things that you enjoy and that you find yourself attracted to and you get on well with, and there'll be other things that you don't, and that's okay. Most of the modules are fairly swift at this point. Module 4, the machine learning, has got a bit more to it, so it's a little bit longer. But most of the modules are, a couple of weeks, and so, this is a week and a half, this particular module. Having said that, discrete event simulation is typically one of the most popular approaches that are used for HSMA projects. No great surprise when our research team, Pencord, was established over 13 years ago now. When we started out, we were doing almost predominantly discrete event simulation for pathway modeling. So there's a long tradition. We have a long tradition of doing this kind of modeling in our team, and operational research is synonymous with this kind of work. So you likely, I suspect, many of you will find yourself attracted to this. You will probably curse SymPy, that we'll look at this afternoon, initially for being a bit odd. But the nice thing about SymPy is that whilst it may look a bit odd initially, once you get your head around it, you'll discover, well, actually, it's always the same. And so, if I want to build a model, I just use these as building blocks. So there's a quite a steep learning curve to get your head around SymPy initially, but then once you do, you're good and you can create pretty much anything. So, but we'll come on to that later. What we want to do this morning really is talk about what discrete event simulation is. I suspect many of you have never encountered a discrete event simulation before. So we'll be talking about what it is, and you have a chance to design a discrete event simulation this morning as well. Just before we start, also, I want to just flag up, hopefully you've all seen on the Slack channel that we set up a brand new 11th peer support group, RJ McCall. This group, this came about, I sat in at the very start of Sammy's revision session for Module 1 last week, and a number of people fed back that they were feeling a bit lost and a bit left behind. And obviously we don't want people to feel lost and left behind. So the idea of this group is that anyone in the cohort can join it at any time, and you can leave it at any time, and you can dip in and out as much as you want. You are still affiliated to your main peer support group. But if you are struggling with a particular area and you feel like you need to go a bit slower, then you can choose to go into this group. We have made a decision not to award PSG points to this group. You still have your affiliation with your original group, of course. The reason for that is to remove any kind of competitive element. The focus should be, if you're in that group, on making sure everyone understands everything that you're doing, and so don't prioritize getting to the end of an activity. It's much better to try and understand and make sure everybody's on board with everything that you're doing. So hopefully that will help. We've never done this before. Hopefully this will help, but please let us know if you find it useful or not. But I would also say as well, if you can take advantage of the excellent resources and facilities that Sammy's put on. I mean, the revision session last week, I only stayed for a bit at the start and turned off a bit at the end. But from my understanding, a lot of people felt a lot more comfortable after attending that revision session. There will be a revision session for each module, and so in a couple of weeks' time we've got the revision session for this module, which hopefully will be a bit less crammed because it's a shorter module and a bit more straightforward. But if you can make it to those, if you are struggling, it's well worth doing that. But even if you can't, check out some of Sammy's excellent resources, particularly for the module we've just completed, that online book full of solution videos and extra materials and extra exercises, and ditto with this. So after the session today, Sammy will share an equivalent book which is developed for this, and it's an excellent revision material if you want to look at things in a slightly different way. A lot of it's just drawn from the lecture slides and stuff we've gone through, but added to and sort of made a bit more readable for that kind of format, but with lots of extra little bells and whistles too. And you may well find that a really useful reference to for looking back over this stuff. So do try and check that out. The last thing I just wanted to mention as a point of housekeeping, as a reminder, next week is a study week, so there will not be a session next week. I had a couple of queries about if you should be sort of studying anything specific. No, so just to be totally transparent, the reason it's a study week next week is because I'm on leave. I think Sammy's on leave too as well. So we have to take leave too, so that's where the study weeks are. So you know where we're taking study weeks. We've got the same in August around the bank holiday. There's a couple of weeks there. However, your organisations have committed to release you for a day a week, and so if you're able to, I'd advise using next week to go back over anything that you feel you need to go back over. So have a look back through some of the slides, look over Sammy's reference materials, etc. And it's a really good opportunity to just try and get your head around anything that you felt needed a bit more, you need to look at it a bit more. Particularly this afternoon, there's going to be quite an information overload. The good news is that you've also got a really long exercise this afternoon, which will give you a chance to keep looking back over it and try it out. But you may still want to go back and look at it a few more times, and so next week hopefully would be a good opportunity for you to do that. So I will post out tomorrow the instructions for the following session, but that will be in 2 weeks' time. There will be no session next week. Okay, let's start. Let's talk about discrete event simulation. So discrete event simulation, which is commonly abbreviated to DES or DES, is basically a modelling approach that uses a simulation, and it allows us to model what we call queuing problems. And basically queuing problems are just things in which we've got things which can be anything, but are usually people, but they don't have to be, that are waiting for some kind of service or services to happen. And in a discrete event simulation, we basically have entities, these are our things, that are flowing through and queuing up for discrete sequential processes. So individual processes that happen one after another. And each of those processes will use one or more resources. Okay. And hopefully in that description, you can see why this is quite a good match for a lot of pathways that you might have in your own organization. So the queues that the entities are entering might be physical, so it might be literally people standing in a queue, but they can be more abstract as well. So it could be a queue may represent people on a waiting list. It might represent people waiting for an appointment, etc., or waiting on the telephone. It doesn't necessarily have to be people stood in a queue, although often it is as well. So because this is a way in which we can model entities that flow through discrete sequential processes. Each of those processes needs resources. Then this allows us to model things like patient pathways. We can model things like telephone systems. When somebody calls up and they go through different options and then they're waiting on the phone, we can model things like the transit of test results and how test results work their way through a system, and lots more. But patient pathways is a big one, and most uses of discrete event simulation, both in HSMA and the wider team, have focused on that kind of modelling. And I suspect many of your HSMA projects will indeed start to look at patient pathways. That's my prediction. Now, discrete event simulation models, because of this, are really useful for asking those kind of what-if questions about changes to a pathway or changes to a process. So you remember back in one of the early sessions, we talked about what-if analysis. We said that you have this idea, you have a base case scenario of what's happening now, and then you adjust that virtual representation of your system by asking what-if questions. So, well, what if we did this? And so in DS models, the what-if questions are around, well, what if we changed the pathway in this way? What if we added these kind of resources? What if we took them away? What if we had people going here and then there? All that kind of stuff. So here's an example of a system that might be modelled using a discrete event simulation approach. So we've got a simple ED system here where we've got patients arriving at the ED, they get booked in by a receptionist, they're triaged by a nurse, and then maybe no further action is taken, they leave, or maybe they need to be seen by a doctor. If they're seen by a doctor, then they get treated and they need a cubicle for that, and then they might be admitted, or they might get discharged, or they might die. If they're admitted, then we need a hospital bed, and then they might die, or they might get discharged, and all this kind of thing. And you can imagine this is the kind of pathway that a discrete event simulation can tackle. So various components make up a discrete event simulation, and there's various terminology that we use in order to describe these various bits of a discrete event simulation. So the first thing I'm going to talk about is entities. So entities, as I mentioned before, they're the things that are flowing through your system, flowing through your pathway. So in a lot of cases, there will be patients, but they don't have to be. And as I say, depending on what you're modelling, your entities could be test results, or it could be callers on a phone. And you can have more than one type of entity in a discrete event simulation. So you may be modelling patients and phone calls in a different part of the system. We also have these things called generators. So generators are basically the way in which our entities enter our model and come into being. So how they're created in our model. So if we're modelling an emergency department, it might be that we have a generator to represent patients arriving at the emergency department by ambulance. We might have a different one to indicate these are patients who are self-presenting at the emergency department. We might have a third one that says these are patients who are referring from being referred from a GP, etc. So we may have just one, we may have more than one, depending on what we're trying to capture and the questions we're trying to answer. And sort of in line with that is this idea of inter-arrival time. So basically an inter-arrival time simply is the time between entities being generated in the generators. In other words, the time between our entities arriving into the system. So it's patients at an ED, it's the time between patients arriving, one patient arriving and then the next patient arriving. And because of that, you can have different inter-arrival times depending on their mode of entry. So this is a good tip if you've got, if you're trying to think, well, do I need to represent the different ways in which patients arrive at an ED? Well, the answer is, if they have different inter-arrival times, then yes. If patients are coming in more frequently by ambulance than they are self-presenting, or vice versa, then you'll probably want to capture that. So you can have different generators, different arrival points with different kinds of inter-arrival time profiles. Then we've got these things called activities. Now you also sometimes hear them referred to as servers. I tend to refer to them as activities, so you won't hear me refer to them as servers, but in discrete event simulation there is a concept known as a server. It's basically just an activity And these are basically the bits of process that your entities are queuing up for. So things like triage or booking in at reception or speaking to the doctor, those bits of process, they're the activities. Okay, so you've got your entities, the thing, usually patients, but not always, who are coming into your model via generators. And the rate at which they're coming in is determined by their inter-arrival times, the time between one entity arriving and the next. And they're basically going through and they're having these activities done to them. Now, associated with activities, we have this concept of activity time, and basically it's fairly self-explanatory. The activity time represents the amount of time that it takes for an activity to happen to that entity. Now, normally, this is stochastic, i.e. random, and normally we draw that from some kind of distribution that represents the variability in terms of time that they would spend in that activity. And that's the same for inter-arrival times as well. They're typically stochastic. Not always, but typically they are. And so this allows us, if you remember back to one of the early sessions where we talked about the concept of distributions, why we use them to capture variability in real-world systems within a model, this is where we use them. And so we can say, okay, I'll sample from this distribution to determine how long this particular patient is going to spend with the nurse, how long this patient will now spend with the nurse, how long the patient will now spend being treated, etc. So as well as activities, we also have resources, and resources are basically the stuff and or staff that are required for an activity to happen. So if you've got a triage activity, it might be where you need a nurse resource in order for that to happen. It might be if you're for the treatment activity, you need a bed to be free. You may need a consultation room for a GP to see the patient. You might need for an X-ray, you might need to say, well, we need both a radiographer to be free and there to be an X-ray machine, etc., etc. It's important to note that resources might be, and often are actually, shared between activities. So a nurse resource may not be just triaging, they may be doing other things in your model as well. And they might also be doing things that aren't in your model, but will be taking their time away. So it doesn't mean that you, just because they're not doing it in the model, they're not doing it. And it's important to capture that. And later on, we'll come into, in fact, next week, we'll have a proper look at how we do that in Discrete Event Simulation in SimPy. But you need to be careful that you don't create a model that's not capturing unavailability of your resource. It's also important to think that you don't have to capture all of the particular resources that you need, just the ones that are both resource constrained and relevant for what you are doing. So, if you thinking, well, I need this staff member and this bed to be free, that's a valid resource, but not, well, I also need a pillow and a sheet. You're assuming that comes with the bed and they will be available, etc., etc. So think about whether it's constrained and whether it's already captured in what you're trying to model. As well as activities, of course, we also have queues, and this gets to the heart of a discrete event simulation, because queues are where our entities wait in order for the activity to happen. And they basically wait in that queue until the activity has the capacity and the required resources in order for that activity to happen to that particular entity. So it might be that if you're a patient, you're waiting the queue to be seen. You're waiting for a treatment cubicle and a doctor to be available to be seen. And then we've got, much like we've got generators that bring our entities into being, our arrival points in our model, we also have exit points, and these are known as sinks in discrete event simulation, and they're basically just how our entities leave. And it's important to note that just because they're leaving your model doesn't necessarily mean they're leaving the system entirely. They're just leaving the bit of the system that you're modelling, but they may still be in the hospital, for example, if you're modelling an ED, or they may even, it might be even simpler than that. You're just modelling one part of an ED, and they've just left your bit of the model. But that's remember we talked about this idea of scope when we talked about conceptual modelling, determining where the barriers are, which slice of reality are you going to carve out to model. This is where they leave it on the other side, and the generators are where they come in. So it's where they enter the bit you're modelling for a generator, and where they leave the bit you're modelling through a sink. So basically, the structure of a discrete event simulation is as follows. We've got one or more generators that bring our entities into being. They then flow through and queue for these discrete sequential processes, these activities. These activities have various resources associated with them in order for the activity to happen. And at each stage they're queuing. They might go down different pathways depending on various things, and then eventually they'll hit a sink and leave on the other side. And that's basically the basic framework of any discrete event simulation. So going back to the example we looked at a moment ago, if we think about this in terms of discrete event simulation language, we've got patients arriving in an ED, that's our generator. Then we've got our first activity here, patients being booked in, that needs a resource of a receptionist, and they will queue until a receptionist is free. And then they go through these activities here. They might branch off down into sinks if there's no further action, or if they're discharged, or if they die. And we'll also have our inter-arrival times will be the times between patients arriving at the ED. Our entities will be patients, and each of those activities would have an associated activity time that will be drawn stochastically. Okay, so let's talk about each of these things in a bit more detail. So let's start with entities. So each entity may have certain attributes that it carries with them, which help to determine the way in which it flows through a particular system, its kind of journey, if you like. So it may carry information that determines whether it goes down this path or that path, or how long it's going to spend in an activity, or what its priority may be for a certain activity. And as I mentioned, there may be more than one type of entity in your model at a time. So you might have in a clinic, you might be modeling patients, but you may also be modeling their test results perhaps as well. It depends on where, how you've designed your model, and also phone calls into the clinic as well. And they would all be separate entities that would be modeled separately as well. So this idea that you've got, when we talked about object-oriented programming last week, hopefully this afternoon you'll see this starting to come make a bit more sense, because we can imagine the concept of a patient, and that patient is carrying attributes with them, information about them. So maybe this patient has a priority attribute, and theirs is set to high. They're going to be streamed down the major stream of the emergency department, and maybe their probability that they will get admitted is 80%, or something like that. And because their priority is high, they maybe jump the queue, and they'll go down this part of the pathway because of these attributes, etc. Now we're talking about generators. Generators are the things that are bringing our entities into being in the system, and we said that the rate at which these new entities come into being is determined by our inter-arrival times, and basically that's all inter-arrival time is. It's just determining the time between one entity arriving and then the next entity arriving from that generator, that specific generator. Now sometimes these inter-arrival times are fixed. And sometimes you have the things are coming in at very specific intervals, but often, and in most of the systems you will model, there will be randomness, and they will be stochastically drawn from a distribution in order to capture some kind of variability. And that variability may be very, very small. It might be that patients on average come in every 8 minutes, and it tends to be that most patients arrive the inter-arrival time is between 7 and 9 minutes in most cases. It's not a huge amount of variability, but it can make a massive difference to your system. And if you don't capture that variability, that can have knock-on consequences. So you should always be capturing variability wherever you can. Now, typically, in order to capture the stochastic nature of inter-arrivals, we tend to use an exponential distribution from which we sample inter-arrival times. Okay, and in most cases, an exponential distribution will give you what you want. It's very good at representing the time between discrete events happening. In this case, it's independent patients who are arriving one after another. But you might find that you use more than one distribution or more than one representation of the exponential distribution for the same generator. So it might be, for example, that at different times of the day, patients will arrive more frequently, or for different days of the week, they will arrive at different intervals. And you can do that. You could use an exponential distribution, but just plug in different numbers as the kind of the average time that they're arriving. And that will sample from a slightly different distribution. And of course, you may have more than one generator in the system, and each of those may have their own inter-arrival times as well. So just to spell out how this is happening, imagine we've got two generators here, but we're just going to look at this one here, arrivals to the clinic. Basically what we're going to do is randomly sample from this. This is an exponential distribution. We're going to randomly sample the time to the first arrival. We wait for that to happen, wait for that time to elapse. Once that's elapsed, we then generate an entity. That entity comes into being. Then we're going to randomly sample the time until the next patient, and then we'll wait until that time has elapsed, and then we'll generate the next entity, etc. And we basically just go through this process of sample the time until the next patient arrives or next entity arrives, and wait, and then when that time has elapsed, create the entity. Now sample the time to the next one, etc., etc. And basically that's all a generator is doing. So we also talked about queues. Obviously, queues are a fundamental component of discrete event simulation. They are effectively queuing models, and so it's no surprise that queues are such a fundamental part of that. And so each activity within a discrete event simulation has, by implication, an associated queue. And the queue is where your entities are going to wait whilst they wait for that activity to become free, so that they can enjoy that process. Now, each queue has its own queuing policy, and basically a queuing policy simply determines the order in which our entities are released from the queue into the activity. Now, there are lots of different types of queuing policy. However, by far the two most common that you will use are these two. So the first one is FIFO, which is first in, first out, which basically says entities are seen in the order in which they arrive. So a patient arrives first, they're the first one to be seen, etc. This is the default. Okay, so for a discrete event simulation, FIFO is always the default. SymPy, if you don't specify anything else, that's how SymPy deals with queues. It will just assume, well, that patient arrived first, so that patient gets seen first. However, obviously we are often dealing with queuing systems in which that may not be the best policy for all of the queues. In some cases, there may be some sort of priority-based policy in effect. You know, you don't, if you're waiting at an ED and somebody turns up with a life-threatening condition, you don't say, "Oh, I'm sorry, there's 27 people in front of you, we have to see them first." They get moved up. And there'll be a lot of situations where you're looking at, people may get bumped up a waiting list because of their condition, etc. So we can use something called priority-based queuing as well. And that's where we basically release our entities from the queue into the activity based on some kind of priority attribute. And usually if there are ties, then we use FIFO. Now, as well as queuing policies, there are also various kinds of queuing behavior And queues are a fascinating thing themselves. There's a whole field of queuing theory that delves into a lot of this. But the key thing to remember is that not all queues run as planned. And very often the things that are queuing are people, and those people will choose to behave in certain ways. And even when it's not people, certain things may change the course of what's happening. It may not be that an entity enters the queue, waits, and then the activity happens. Stuff might happen along the way. So we've got these three main queuing behaviors here, known as reneging, bulking, and jockeying. Now, reneging basically refers to when you've got an entity that removes themselves from a queue after a certain amount of time has elapsed. So it might be that a person's queuing up for something and they're not willing to wait any longer, so they leave the queue. Very common in things like phone systems where people are waiting on the phone and think, oh, I'm not waiting any longer, and they hang up. That's an example of reneging from a queue. However, it might not be people, it might be things like, you may have a test sample, and that test sample, after a certain amount of time, may not any longer be viable, and so it is removed from the queue. It is no longer of any use. So that's reneging. It's basically saying, I've waited long enough, I'm not waiting any longer, I can't wait any longer. Then we've got bulking. So bulking basically refers to an entity that never enters the queue in the first place, because of typically the length of the queue or its capacity. So, the patient, somebody may see a queue and think, oh, I'm not waiting that long. Or sometimes, on a phone system, you phone up and they say the waiting time is 50 minutes or whatever, and you think, oh, I'm not waiting that long, and you put the phone down. So they never join the queue in the first place. It might also be due to capacity, so maybe there's only so many people that can fit in the waiting room or something like that. So bulking is where you never join the queue. And then we've got a third behaviour here called jockeying. And jockeying is basically where you have an entity that switches between queues because they're trying to reduce their queuing time. And this is, you will commonly see jockeying behaviours in a supermarket, for example, where you're queuing up and you're looking at that queue and thinking, that queue's moving much faster than this queue, maybe I'll go over to that one instead. And so you switch queues. That's known as jockeying behaviour. Okay, so in this example here, where we've got a fictitious audience with Dan Chalk, clearly none of these behaviours would ever happen apart from jockeying, I'm sure. But in this example, we may have people who are reneging. They say that they've waited long enough, they're not going to leave. They're not going to queue any longer. Bulking, they're looking at the length of this extensive queue and thinking, I'm not bothering with that. And then jockeying, where they're trying to get tactically to the front of the queue to get seen quicker by switching queues. So in terms of our activities and our activity times, so each activity in a discrete event simulation basically describes a process, and it might be that's a really simple atomic task. It might be, take blood from patient, for example. That might be a process. But it might also be that your activity represents a set of tasks bundled together. So to give the triage as an example, so again, it goes down to the conceptual modelling stuff that we talked about earlier in the course. What's the level of detail that you need in order to answer your question? What's the minimum level of detail that you need? So it may be that for your model, you just need to describe triage as triage, but it might be that you need to break that down. So it could be that triage involves, the nurse checking your blood pressure and taking bloods and doing all these little things. So you need to decide, do you need to model all of those individual things, or can you just simplify this down to the nurse will do all of this stuff with the patient and it'll take an amount of time. And in most cases, that's probably the level at which you would be operating. But again, it depends on what you're modelling. If you're modelling, in that example, let's say you were trying to model something around the delays to the blood test being sent off, that may well be the bit of the process that you want to separate out. Now, for an activity to take place, we said it needs basically two things. It needs an entity to be waiting in the queue, and it will get pulled in for that queue according to the queuing policy. And it requires the required number and type of the associated resources to be available. And then once both of those conditions have been met, the activity can then begin. Once the activity begins, the entity and the resource or resources that it needs are then locked in place for an amount of time. And this is known as the activity time. And this is important because whilst this is happening, the resource or resources that are being used for that patient or that entity cannot be used elsewhere. Now that makes sense if you think about it, because if you're, again, going back to the triage idea, let's imagine you're in the ED, you need the nurse and perhaps a bed in order to be, or treatment cubicle, I should say, to be triaged. And the nurse can't do both things, or you can't have the nurse doing something else with this patient at the same time. So they may be flitting back and forth and coming back to do a second process with you, but they can't do two things simultaneously. So when that patient or when that entity it goes into this activity, they essentially get locked in place with that resource. So that resource is now not free to do anything else. Now, activity times might be fixed. Sometimes there are cases where things will take exactly this amount of time. However, that's generally quite rare. In most cases, you would have an element of variability, and your activity times would typically be sampled from a distribution. And just as with arrival points, inter-arrival times, we said that they are typically in a discrete event simulation, we use an exponential distribution to represent them. For activity times, we tend to use log normal distributions. Don't worry, we'll talk more about exponential and log normal distributions as we move on. But log normal distributions are very good at representing the variability in activity times in discrete event simulations. So if in doubt, exponential for your inter-arrivals, log normal for your activities is basically what most of your models will look like. However, a small caveat there, one little tip really, it's often easier to, when you first start with your model, to make everything an exponential distribution, so inter-arrivals and your activity times. Now that won't be as realistic, but an exponential distribution is much easier to adjust and play around with, okay? Because for an exponential distribution, you just specify, well, you specify lambda, as you saw last week, but lambda is just 1 over the mean. So all you need to know is the mean. So in other words, you can be working with your stakeholders and say, okay, well, how long on average does a patient spend with a nurse? How long on average do they spend with the doctor, etc., etc.? That's an easier question to answer. Log normal distributions are a bit more complicated. So it's easier to adjust an exponential distribution. You also have to do something in SimPy, which we'll show you, to translate a log normal distribution. They are a bit more complex. So good practice, good little tip, start everything with an exponential distribution because they're easier to understand and play around with. And then once you're happy with the model, switch over your activity times from exponential to log normal and just keep your exponential distributions for your generators, for your arrivals into the model. So just to hammer home this point, let's imagine we've got a GP consultation as being our activity. Our patient has arrived, our GP is ready, this activity can now happen. We randomly sample an activity time from a log normal distribution. This is a log normal distribution. Once we've worked out how, so that will basically determine how long is this patient going to spend in this GP consultation. Let's say it's then 7 minutes. We then start the GP consultation, and for the duration of that activity, for those 7 minutes, both the patient and the GP are held in place. They are locked together and nothing else can happen to them. Okay, that represents our activity. Once that activity is completed, that time's elapsed, the GP and the patient are released. So the patient will then go on, if there's any other activities, to go on to those. If not, they'll leave the system, and the GP is then free to do other things or see the next patient or whatever it may be. So I keep mentioning about the importance of resources in discrete event simulations. Resources are basically needed to undertake your activities, and an activity may require just one single resource, or it might be you need more than one of the same type, or it might be you need multiple resources of different types, like you need a bed and a doctor, or whatever it may be. Some activities may not require any resources at all, but if you are coming to that conclusion, just check very carefully that that is true. It doesn't have to be completely resourceless in the real world, because very little would be. But is it resourceless in the context of your model, i.e., the constraint? There is no constraint effectively for the purposes of what you're modeling. So if you know you'll always have enough seats in the waiting room, and it doesn't matter because people will just stand outside and wait. If not, then you don't need to model seats in the waiting room. That's resourceless. So your resources can be things like staff, so doctors, nurses, police officers, whatever it may be, and stuff, so things like beds, test equipment, detention cells, if you're modelling a policing system, etc. And resources can, and as I say, often are, shared across the system. So just because a nurse is doing this thing over here, they might be doing something else in your system as well. And so the activities will be essentially competing for that resource's time. And so a problem in one area of your system can affect another area of your system. And this is where you start to get the advantage of discrete event simulation, because you're getting a bottleneck here, and that's having a knock-on effect over here as well. You need all of the resources that you've specified in order for an activity to happen. In some cases, you can have situations where you can have more optional resources, and if you've got those, then the activity may be sped up, although it's rarely linear. I wouldn't worry too much about that. There aren't that many situations where that would occur, but if you do have a situation like that, you can model that in discrete event simulation. Now, I've already talked about how resources might be unavailable because they're off doing something else in your model, because they're needed for different activities. But they might also be unavailable for other reasons. They might be needed in areas of the system that we are not modeling, and we don't have to model everything. We talked about that earlier in the course. We only want to model stuff that is relevant for our question. What's the least we can model to sufficiently answer our question? Or it might be that they're not working anywhere, that they might be off shift, or that if it's a piece of machinery, the machine's broken down, for example. So as a modeler, it's your job basically to determine what happens when that resource is unavailable. And the way you do that is by working with your stakeholders in your real world system. You find out what happens when there's different levels of resource availability. Do entities then queue if you've got a clinic and there's a doctor and then the doctor's on lunch, people wait until the doctors come back. Is it not a problem? Because actually when the doctor goes on a break, another doctor is there and they take over, so you've always got a doctor, or always got two doctors, or whatever it may be. If it's the latter, if you've always got a doctor, even if it's a different doctor in practice across different points of the day, but if there's always one doctor, then you can just model that as being one doctor. Doesn't matter who they are. The fact is there is one doctor resource always available. Now we'll come on to this not next week, the week after, when we look at this in a bit more detail. But when we're modeling in SimPy, we can model resource unavailability quite simply, and basically the way we do that is we have this activity that gets the number one priority, and basically it grabs them away for an amount of time, and that captures the resource or resources not being available for whatever reason. And of course, just once the entities have gone through all of our activities and had everything done to them, they will leave our bit of the system in various different ways, and that's where our sinks come in. And remember, a sink is just the way in which they're leaving the bit of the system we're modelling, not necessarily leaving the real world system as a whole. So it might include things like the entity physically leaving the system, so they're discharged from the hospital. It might be that the entity no longer exists, so the patient's died, or the sample, if it's a test sample with the entity, the sample has been used, or if it's telephone calls you're modelling, the telephone call has ended. It might be that, and in most cases, the third one will apply where the entity is just no longer accessing the bit of the system that we're interested in. So it just leaves our section of the system, basically. And that's the most important thing to remember. That it doesn't necessarily mean they're leaving the real world system. It means they're leaving your slice of reality that you're modelling. Now, of course, so far we've talked about fairly linear paths, but in reality, most often we will have branching paths. Different things will happen to entities, say patients, depending on whether certain things are true. And we can model that in a discrete event simulation. It basically just means that patients or entities flow to different activities or flow into different sinks. And it might be that we differentiate based on some attribute that the patient's carrying with them, i.e. higher priority patients might go down one route as opposed to another. Might be based on probability. A lot of cases our paths are based on probability. So we say, okay, when the data, 20% of people go down this route, so in our model we'll capture that as, we'll randomly select 20% of them and they'll go down that route. That's most commonly how you do branching paths in discrete event simulation. Or it might be based on time. So we say, well, we're modelling a 24-hour system, but overnight they go down this route, and so we check the model time and say, well, if the time is between this and this, then they'll go down this route instead. So there's lots of different ways we can do that. And as with any kind of model, whenever we're building a model, we need to think about what we're trying to achieve by building that model, and that will help us determine what our outputs should be. And because a discrete event simulation is primarily used to model queuing problems that have associated resources, typically a discrete event simulation, it would depend on what you're doing, but typically a discrete event simulation will include things like average, minimum, maximum, 95th percentile of things like how long are our entities in the system? How long do they spend in ED, for example? How long do our queues get on average? What's the maximum? What's the biggest kind of queue? What's the shortest queue? How long are patients queuing for? What's the rate of resource utilization, i.e. the percentage of time that a resource is in use, particularly if you're modelling things like beds. What's your bed occupancy? That's resource utilization, basically. You don't necessarily want it too high, because if anything goes wrong and you suddenly get a spike, you've got a massive problem. Or you might have things like the probability that you exceed a defined threshold. So what's the number of patients that come through the model that are predicted to breach the 4-hour wait in ED, or there's too many people in the it's about when we had the COVID modelling, there was a lot of stuff around overcrowding, having too many people, and so Adam, who developed the fantastic vaccination model in HSMA3, looked at that and had that as one of the outputs. What's the percentage of time at which the waiting is going to become overcrowded and therefore breach social distancing and all that kind of stuff. Okay, so there's quite a lot of information to take in, but broadly speaking, discrete event simulations, you have generators that bring your entities into being. They then go through a series of activities, things that happen to them. They queue up for each of those activities whilst they wait for the associated resource to be free. And then on the other side, they leave in some way via a sink. And that's basically how they work. Sammy, are there any questions that have come up as a result of any of that?
So I have got to most of them in the chat, but the two I haven't managed to get to yet are can discrete event simulations loop back on themselves? So almost like a while loop or some sort of until statement. So that was one of them.
So I think you mean. I'm guessing what you're getting at is, can a patient sort of leave and then they come back into the system, if you like? So the way you would, I won't get into the details of how you do that yet. The way you would typically do that is not by having, so much in the same way as I just mentioned about resources, that you may have one GP resource, for example, but it might be in reality it's lots of different doctors at different points of the day, but you're just modelling the fact that there is a doctor, one doctor available. In the same way, don't get too hung up on individual patients necessarily representing being that individual patient. So they are for the purposes of how they flow through a system, but there will be different ways in which you would approach that if you wanted to get them to come back in. And one of the simplest ways, very often, is to sort of record that this patient has left, but there's a chance that they come back in, and then that affects the inter-arrival time coming back in. So maybe strictly speaking, it's a different entity in terms of the model, but it's basically representing that patient coming back. So I realise there's a slightly complex answer. It will make more sense when you see how SymPy is structured. But yes, you can have people coming back in, and you could have people just looping back round. I'm also aware you might also be referring to something that will come on. Well, in fact, we won't come on to, but Sammy's got some stuff in her reference materials. There's something known as a governor model, a governor approach in discrete event simulation. That's where you have things where you say, okay, I've come in now. I may go over here and have this test, and then come back over here. Then I might go over here and do this, and then that thing might happen, and then I might go over here. And you kind of have this the idea to how to represent that is you have this kind of central governor that decides the kind of sequence of events for that particular patient or that entity. So that's another way of looping back around if you're trying to capture a system where they might be going back to a waiting room, for example, and then different things might then happen, but they keep going back to a particular process. So that where you've got that kind of situation, that's where you tend to use a governor type model. Again, all this will make more sense when we start to see them.
Brilliant. And the other one I've got is so on the subject of branching, could patients go into paths simultaneously? For example, could they access a system, sort of an entry point system, and then be seen by multiple services within the system, such as say physio and complementary therapy? But so they could be waiting simultaneously for both of those things to take place.
Yeah, so you can have that. There's a thing in discrete event simulation where it's called batching, where you can basically split up your entity, almost like you've torn them in half, and they go down different routes, and then you reassemble them the other side. So you can do that, yes. We won't cover that in this course, except to say that probably from the description in that question, the governor type approach would probably work best for that. But yeah, you'll see. So the beauty of SymPy is that it's built around this idea of a generator function, which we'll come on to later. Once you get your head around that and how SymPy is structured, you can basically do anything because it's just in Python. This is why we teach you the free and open source approaches, because you can code anything you like. You're not restricted. So basically, SymPy gives you the advantage of you don't need to code from scratch an entity is, what an activity is, what a queue is. It knows what all those things are, and then you can build anything you like around that. But a lot of it will come down to how the most efficient way to design stuff like that. And it depends how you break down and conceptualize your model. But again, some of that will make more sense as we start to see these things in practice as well. Were there any other questions, sorry, Sammy, or was that it?
No, I think that's all the ones I hadn't managed to get to in the chat. So good to
Okay,
go.
great. Excellent. Okay, cool. So we will stop there and get on to your first exercise of the day. Now, you've got two exercises today, and both of these are long exercises. So you have lots of chance to take this slowly and to try and achieve what we're setting out here. So for this first exercise, what I want you to do is go into your groups, and you're going to design a discrete event simulation for any system you like. Okay. So the first thing you should do is in your team is have a chat about what that system might be, and it could be absolutely anything. So it doesn't have to be health or policing related. It can be anything you like. You can create a discrete event simulation of a restaurant or an airport or a customer service telephone line. It doesn't matter. Just think about any problem where there might be essentially a queuing problem. Then you should decide as a group which one you're going to look at, and what the fictitious what if questions are that you would ask the model if you were to create a model of this. Now, I'm not expecting, if you decide to design a discrete event simulation of a local restaurant, I'm not expecting you to go off now and speak to that restaurant and find out what the process is. A lot of this is going to be a bit creative and making things up. Okay, it's just to get you into the habit of how you might translate this into a discrete event simulation. So once you've decided what you're going to model and what the fictitious what-if questions will be, you're then going to draw up a design for the model. And that design should include, first of all, the what-if questions that you're going to use your model to answer. You're then going to build a process map. Again, you'll probably have to make this up unless you happen to know the processes, all of the processes of the system that you're looking at. But a fictitious process map of the system that you're modelling. And then the third thing is a conceptual model of the proposed discrete event simulation. And bear in mind what we talked about in our conceptual modelling session, where we said not everything that's in the process map gets translated into the model. So the idea of the process map is to capture everything that happens, but then depending on what your what if questions are, you then need to decide, but what are we going to model? What's the level of detail we need? Where do we put up our boundaries? What's the scope, etc.? What sort of level of detail? What is this high level? We're going to model it low level, etc. So identify what your types of entity or entities are, the generators you might have in your system, the activities, the queues, the resources, the sinks, etc. Describe what each of your inter-arrival times and activity times are representing, and where you might draw that data from if you were building this for real. So again, remember the training from this earlier session 1B where we talked about scope, level of detail, all of these things when you're building a conceptual model. You're again, just to really hammer home the advice, typically you want to build or design the simplest model that answers sufficiently your question. So I'm going to give you an hour and a half to do that. So you've got until 12 o'clock. And make sure you take some breaks. I'd probably take a break now if I were you, because that was a lot of information to take in. But you probably want to take another break in there as well before we come back. When we come back, I'm going to ask each group to present their designs. You'll have just a short sort of 1-2 minute slot. And Sammy will then judge the top 3, and you'll get some PSG points for that. And just to reiterate, so with the RJ Macau group, again, I'm going to try and be as flexible as possible on this. So if you I will ask you if you want to present, basically. You don't have to, because remember, the objective is for you to understand what's going on rather than present. But of course, you are very welcome to do so. So you'll always have the option of presenting, but you won't be forced into doing that. Okay, great. I will stop sharing there. Go and take a break, though, right now. I'm going to stretch your legs. And then join your groups. And I'll see you in an hour and a half. Sammy and I will be floating around.
Hello, everyone. So Dan is going to be back in a moment, but he's asked that I just get you all back into the room and kick off the presentations. So I have started the recording, and I will just start going through in alphabetical order this time, if that is okay. So Agnes, are you ready to present?
Yes, let me just share my screen. One second. Do you let me know if you can see that?
That's coming through, yeah.
Okay, cool. So our simulation model was a car wash, and the output we were interested in was how to keep the queues for cars under 4 cars long. So it was split into 3 main portions in terms of the process steps we modeled. So there was a car arriving to the car wash, the car being cleaned depending on the cleaning requirements, and then the car entering the sink and leaving the system after the person pays. In terms of entities, those would be cars, and it would be different depending on the size and the type of vehicle. And in terms of the resources and the constraints we had to model for this, we had washing bays, car park staff needed, and space to park whilst cars were waiting to be cleaned. And in terms of like resource consumption, a lorry, for instance, would need more time in the washing bays or would need a larger number of washing bays than, let's say, a small vehicle. The entities, we tried to incorporate some object-oriented programming into how they were modeled. So there was a vehicle parent class, and then the different types of cars were childs of that class. And, one attribute would be the size, cleaning requirements, whether or not the person had booked in advance. So we've got like the different conceptual model aspects as sticky notes, and then the steps in the process are each of these colored blocks here. So yeah, that's our car wash model.
Fantastic. I really, really liked seeing when I popped into your group as well, the fact that you were thinking about how you could use that, the inheritance, etc., of the classes. That was really good work on bringing together those concepts from the last session as well. Thank you very much. Dan, do you want to take back over, or should I carry on running this bit?
Yeah, I'm very happy for you to carry on, Sammy, for a moment. Thank you.
Cool. In that case, let's go on to Antic. We have a representative from Antic here.
I assume I'm presenting then. Okay. Share the screen. Okay, so we decided our system that the DES we want to create will be a nice fun fair, that we have a little bit of activities going on. We looked through a different kind of questions of what if our ticket systems, if we have more rides, what if staff is restricted, or what if the season changes or people get injured at any given time. We then proceed using those to create a little bit of process mapping to look at different activities and entities, with the customer arriving at the gate, maybe some kind of gift shop, food stall, toilets, ticket booth, and ride activities itself. We labeled them with different kind of colors, which then we reconstructed into a whole process map of one-way system to begin with, which we have when which keep saying page for some reason. When customer arrives, they will then queue for a ticket booth, which is then manned with the staff and number of tickets, and they could potentially exit the system if they are bored, which is renaging, or if the ticket have reached the maximum capacity and they were turned away. Then after that, they would go to a ride 1 and 2, which we have staff and potentially limited number of seats for any given ride, going to the games with the staff and the prices, as well as different areas that they can potentially go individually, and then exiting the system itself. We also considered that our entities within our system, which is our people who are going to have fun, have different kinds of attributes. So we separated our generation into the people who might walk in, magically appear, or drive in to the gate of the fun fair, which has the attribute of inter-arrival times between when people will arrive there. Then we have our queue, which we've broken down to the waiting time for tickets, rides, games, and independent activities such as toilet booths, and gift shops. For the entities, we say that we could have them as adults or children, till we separate them into different categories, and height for safety for any given ride. And if they're thrill seekers, they might want to seek for a particular activity within the fun fair. And if they have pre-bought tickets, then they could potentially cut the queue to the ticket booth. We then have our activities as the ticket booth, rides, toilets, and as we mentioned before, they have each activity times and resources needed to operate them, such as the number of staff or staff time in there as well. We then have our resources broken down to independent parts, staff, tickets, prices, cleaners, food, gift items, seats per ride, which are then consumed along with the activity itself. Then we had our sinks. We thought that we might have 3 different types. One is they will exit at the very start or exiting our whole fun fair system, or at any given time if a customer gets injured, for example, or if they just want to leave. Data we thought could get from website or fun fair sales or some other areas. We then also looked at the system of what if there is no linear path and they can go anywhere they want. To answer our question with modeling, we then thought to simulate perhaps one of the parts, such as what if we change the ticket booth staffing level, can have a different queue which they can pre-buy the ticket, how that would affect our system.
Fantastic, great work, Amtic. I'm really liking, I thought that was great as well to see that you had thought about where you could get the data from. That was really good to see that in there, and I really like how you had that progression from starting out with that one-way system, and actually then, as Dan just said in the chat, this would be a really nice way to use one of these governor models that he briefly mentioned earlier, so actually having people going back to that sort of central position and going, where am I going to go next? Fantastic, thank you very much. Right. I think next we have got Arm. I may need you to stop sharing. I'm not sure Arm will be able to take over the sharing or not. Perfect, thank you. Do we have someone from Arm?
Yeah, that's me. Hello. I'll just start sharing. Hopefully you can see that.
Yeah, that's come through, thanks.
So we would like to welcome you to our rival theme park, the Star Wars Armada. So essentially, yep, we thought we would have some amazing rides in our theme park, offering lots of activity choice, different things that you can do. And here is our more sort of simple process map. So people would arrive at the main entrance, they would buy a ticket, that may be a fast track or a standard ticket, giving them different queuing times for their rides. They would choose their initial activity, which would have a queuing element to doing that. Of course, people may go to more than one ride, so they would, potentially stay in the park, get to choose other activities and go around different rides, or they could go to a cafe, a gift shop, and then our sync was to be leaving the theme park or the theme park closes. So looking at that in a more detailed model, we kind of layered that then looking at our entities being obviously the people coming into the park, and we would need to establish what the inter-arrival times were of those people. There would be different queuing times between activities depending on whether they had bought a fast track or a standard ticket. So that's our kind of what if in this mapping. And then we looked at different sort of how the impact of different resourcing might need to be put into the model as well. So thinking about rides may have a certain amount of attendance that would speed up or slow down how quickly people come on or off of rides, the amount of people you can get onto a particular ride. And then looking at things like in a gift shop, what would be the flow in that gift shop? How many assistants do they have at the tills that could speed things up or slow things down? And similarly in the cafe, looking at things like how many people can actually eat into the cafe, is there tables, how many assistants are they actually serving the food? So we started to look at some of those resourcing things that could impact, as well as looking at our what ifs in that model. So some of the key what ifs we looked at were just thinking about, you know, is there a fast track system versus a standard ticket, and how would that actually work? What would be the kind of parameters of that? What if we were to introduce queuing at the rides that where there was a queue only for people who are kind of going on their own, which might speed up the flow of getting people onto the rides? And if we increase the number of rides actually available in the theme park, would that reduce queuing times overall? Our generator was essentially people coming in through the gate, so we saw that as kind of one generator. But we talked a little bit about, you know, how at what point would you want this model to start? Could it actually start before people get to the gate, and you could look at different ways that they get into the theme park and build that into the model? But we chose to kind of start out at that entry point into the park. Our entities would be the visitors, of course, but thinking about different groups of that, people who have a fast track, people who are arriving in a group versus individual. So the type of entity that you have might be different. And then looking around the activities, so thinking about, you know, is it a ride-based activity? Is there activity that they are dining, or are they shopping? And thinking about some of those resourcing issues that could influence the time spent in those activities. Our resourcing, again, as we sort of mentioned, sort of the things that might influence there with the number of vehicles on the ride, number of seats in each vehicle, type of food, speed of serving that food. So we felt like those things could all even be separate models potentially, depending on how big you wanted your model to be. And then 2 different queuing systems depending on what ticket type a person has. And then our sync would be essentially people either leave the theme park because they want to leave, or they leave because the park has actually closed. And we might think about a kind of the sort of comparator, I suppose, of an inter-arrival time, looking at an inter-exit time, if that's a term that we can use. Other things that we thought might influence those behaviours would be people feeling the park is too busy and leaving, or deciding to go for a different ride that has a shorter queue. So seeing the sort of jockeying between queues. Or people just actually deciding to maybe walk around the park, go to the coffee shop, buy something instead of actually joining a queue for a ride. And that's it for us.
Fantastic, another excellent model. Thank you very much. Of course, we love the puns here in HSMA. I also really liked I think I came into your room when you were talking about the singles only queue, which was, I learned a lot about theme parks with that. Good to see a mention of first in, first out queuing. I really like the idea of you recognizing the sync of the park closing time as well. That's a really good point, and quite an interesting one to see, you know, how many people are still in your park at that point, how many were queuing, etc., anywhere they got sort of built up. And also really like the recognition of the reneging, jockeying and bulking situations in the park. So fantastic. Thank you very much. Denise next.
Okay, that's me. Okay. Can you see that?
It's just, yeah, that's come through now.
Brilliant. Yeah, so we also did a theme park, which in the last minute we decided to call Anaconda Adventures. So we thought about it as one big diagram. So we looked at the fact that a generator could be airport shuttles or bringing themselves in the car. And that changed the inter-arrival times. So the shuttle would have a group coming at a certain period, and the cars would have variable numbers coming at interval periods as well. And we had the ticket gates as an activity, with the staff being a resource at that point. And then filtering through to this pavilion, which would also have activities built into it, like food courts, and staff as a resource for that area as well. And then similarly, we thought about 2 different rides. So we've got Typing of Terror as our first ride. It's a 4-minute ride, and it's dependent on having an attendant there, and it's got a capacity as well. And ride 2 is our While Loop ride, with ride attendants and ride capacity being the resources as well, and that takes 2 minutes. So we developed 2 queues, a fast track, which would work on a priority queuing system, and a slow track, which would be sort of first in, first out system, with a mean time for those. And then we did exactly the same for ride 2. And when we talked about the fact that this is a very safety conscious theme park. So you always go through your first aid tent at the end as well and make sure no one's had any problems. So the activities are the rides themselves, the resources are how much space in the ride and the staff to run the ride, and the activity time is the length of time that it runs for. And we thought about the visitors themselves, so a little bit of object-oriented programming, but not to a full completion, but the attributes that they would have. So whether they had a fast track ticket, a normal ticket, how old they were, because we've got a 12-year-old age limit on ride typing of terror, it's just too scary. And behaviours such as reneging or bulking, depending on how big the rides actually are. And then we thought a little bit about the staff. So the attributes, so 1 staff member per activity, we've got 6 activities total. So we took a minute to go back to our what if questions, which were, what if we sold 10% more tickets than we currently did? And what if 10% of those were fast track? What impact would that have on the mean times for the 2 rides we have? And also, what if a staff member called in sick? Where would be best to redistribute them amongst the system? That's what we did.
Excellent. Thank you very much. Yeah, I'm really appreciating the more excellent naming of the rides. I think theme parks seem to be a very good opportunity for that. I think, what did I put here? I liked your really nice focused what if questions. That was excellent. And I think the only thing I'd say is you might find that the queue times probably emerge rather than having a sort of average queue time. The queue times will probably emerge from the behavior of the model. So actually, depending on how many people you've got coming into the model, how, that whole ride capacity stuff. So you, instead of having a sort of distribution there, you'll actually see that as an output of your model potentially. But overall, really liked it. Excellent. Another excellent model. So thank you very much. Motorola.
Hopefully that should be sharing soon.
Yeah, that's coming through.
Yeah, so we had a look at more of a kind of like a healthcare based one, because one of our team works in plastics, so we were looking at like treatments and like wound care. So we had people who were coming in through expected appointments as well as unexpected appointments through like a random system. They then went through a reception process and triage. Depending on whether they were high or low severity, they kind of either went to a doctor in a cubicle or a nurse in a cubicle before going down different pathways. We also had a look at people who were kind of like dropping out at different points, either they didn't attend, they didn't want a queue, or they didn't need treatment at all. And we also like had quite a big discussion around how to do the priorities, because you don't want unexpected people just coming in and always pushing people to the back of the queue. So whether we could increase people's priority every 15 minutes so that eventually the people who were low priority would be seen as well. So we went through like the different resources that we'd need. So like receptionists, doctors, nurses, and some kind of like physical room to see people in. The entities would be the patients coming in through the 2 routes. With work being generated either by expected work through appointments or emergency arrivals. And we had like a quick discussion around where we'd be getting the data from as well.
Fantastic. I am really liking that. I think I really like what you were doing as well with the unexpected priorities at the beginning. I think that was a really clever touch, actually, the whole idea of, oh, have I frozen? Or is a sim frozen?
No, I'm still sharing.
Oh, still sharing. No, that's fine. No, just checking. I suddenly realized I looked like I'd frozen or one of us had frozen. And I thought, no, yeah, as I was saying, really like what you've done with the queues there. I thought that was fantastic. The whole idea that actually people could just find themselves at the back of the queue indefinitely if higher priority people keep coming in. I've not seen that approach used before, but that's a really creative way to do it. And I can see that working well. So I also just want to check I didn't interrupt there before you'd finished. I think that was... yeah, you were short and sweet on that one. Fantastic. Thank you very much. Paula, then.
Yeah, I'm up. Hang on. Can you see my screen?
Yep, that's coming through. Thank
Perfect. So here's our presentation. It's called Not a Theme Park, because we're also boring and I'm a clinician, and I don't go to theme parks. So we wanted to create a model which looks at the cancer, so the prostate cancer pathway, and there is a focus on the 62-day target, which is from initial referral from a GP to treatment. Of note, there is a 2-week wait. Referral from a GP is the most urgent referral, so there's no priority in the queue. The problem at the moment is we're very bad at hitting the 62-day target. So we'd like to create a discrete simulation model in order to inform where our most significant queues are in the system, and do a what-if analysis in order to ascertain what resources we could employ to reduce the queues and hopefully meet the targets. So our generator is a GP referral. Our entity is a patient, and we thought that you could then employ the class system in order to give the patients different attributes, all of which would be relevant as they go through the system. Multiple activities, triage, face-to-face clinics, biopsy. The biopsy needs reporting, then the biopsy needs to be reviewed, whether or not they need a bone scan, CT scan, go on to have a multidisciplinary team meeting, and then finally the actual treatment itself. This is resource intensive, requiring treatment rooms, nurses, scanners, more scanners, biopsy rooms, radiologists, surgeons, and theatre space. So you can then imagine there's going to be lots of queues in that, from the initial triage to waiting for the scan, for the reports, for the biopsy report, and so on and so forth. And quite a few syncs as well in there, from decision not to treat, all the way to referral to different teams, and finally to the definitive treatment. And here's an example of some of the what ifs that we came up, essentially increasing the capacity of various bits and pieces. And here is our process map. So GP refers you in, so that's our generator. So triage clinic, decision made, whether or not to go straight for a scan, or whether or not to see someone face-to-face, where a decision is made if they're fit for treatment or not. A sync is if you're unfit for treatment, then you won't get treatment. Once the MRI scan has happened, it then needs to be reported. The report needs to be reviewed. Decision is made whether or not that individual needs a biopsy. A biopsy has to happen. Biopsy has to be reported. Biopsy has to be reviewed by a clinician, and then a decision on the result of the biopsy will then need to be made as to whether or not they need further imaging in the form of a bone scan and a CT scan, which needs to be reported. All of this information is then delivered to the multidisciplinary team meeting, who will then make a recommendation. That recommendation then needs to be communicated to the patient, and then finally the treatment option is decided with the patient going forwards.
Fantastic. Yeah, another excellent model. I can only repeat what Dan said in the chat, that this could make a really nice I can't even remember the name of our own program, HSMA project. Yeah, this is exactly the sort of thing that we would potentially expect to see as a DES project for someone's phase 2 project. I thought, yeah, really nice recognition of your entity and patient attributes, and the importance of all the different resources coming in, as you said, rooms, people, machines. Sometimes it's easy to fall into the trap of it just being people. Really liked your recognition as well of your branching pathways, and I think it's worth recognizing as well, you can get into some really interesting aspects when you start having things like do appointments have to be a certain length of time in the future, so that people actually have time to receive their letters and make plans to attend, that sort of thing. So yeah, really nice. Once again, thank you very much. Who do we have next? That was Paula, so Pokey.
Yeah, it's Pokey. Thanks, Sammy. I'll share my screen now. Screen 2, let's share. So we're back to theme parks. Can everyone see that?
Yeah.
Yeah, back to theme parks again. Okay, let me move on to this part. So we looked at our fairground, what our question was going to be, our what if question, and we wanted to look at the impact of introducing a fast track system and how it would affect the queues. So the metrics you want to look at to see whether this is effective or not would be average wait time per ride, and then we look at the rate of each of the wait time queuing parts that we talked about before, average number of rides visited by guests, so how that affects how many times they actually visit a ride, and then the entities which we decide which rides to visit. So obviously the preference of ride probability. So we talked about making each ride have its own popularity. Sorry, and then whether you can go on the ride or not if you have a heart condition, if you're pregnant, or your height as well for small people or children, I guess. So we looked through all of these all the different parts. So we talked about the entities. So we looked at the guests. So whether a fast track holder, expected duration in park. We looked at the average one as well on the internet, so roughly 7 hours. Height, hunger, heart condition, as we talked about, pregnancy status, how patient they are, and then ride preference. The generator would be the people turning up to the theme park. The inter-arrival time would be an exponential distribution based on time of the day. So at the beginning of the day, you get more people, and then as the day goes on, you get less, because obviously you get less time at the park. Well, that's what we assumed anyway. Activities, so the rides, so the activities would be the rides themselves. Traveling to the rides, we talked about traveling to the rides, then queuing for the rides, and then the ride time, and then the food as well, the option of getting food instead. Obviously that would mean you wouldn't be on a ride and wouldn't be queuing at that point. Resources, so we had the ride capacity, obviously the ride maintenance, because obviously you see a lot of times that rides are down, and then staff, the operating staff and all the different staff. And then we looked at the queue. We think that all of those three, jockeying and all the rest of them would all be part of this queuing. We could see them doing all three of those, and we'll show that in the event in the pathway in a sec. And then obviously the max queue limit, which would be usually at the end of a queue at the end of a day. If you're finishing at 5 and there's a 3-hour queue, then it would have to be closed at 2, because you're not going to get to the end of the day. And then the sync is end of day, like other people have said. And if people just decide to finish and go home, beat the traffic. And then this is our model. As we said, generator, people entering the park, they'll then go through this sort of loop that we have, which is they'll decide the next activity they do, they'll travel to the activity, whether they want food or not, and then they'll decide whether they're going to join the queue or not. So they might look at the queue and go, it's too big, so they'll go back around that loop and choose another activity, or they'll go, if they do, they'll queue into the standard queue or the fast track queue. And then we've just put rides 1 to 4, because that's the group of rides. We'd have lots of different rides there, and each of them would have their own resources in terms of ride operation, ride capacity, and then operating staff. And once they rode the ride, they go back to this beginning part again, and then they decide whether they want to leave or travel to the next one, and so on. And then we talked about our inter-arrival time here as an exponential distribution based on the limit time as well. I think that's it. Thank you.
Fantastic. No, thank you. That's brilliant. I'm really liking, as you say, the time of day affecting the inter-arrival time. That is something I don't think we explicitly cover it in the course, but it is in the accompanying book that we'll share at the end of the day. So this is something that does come up a lot, especially for people trying to model things like emergency departments. So definitely something that's worth knowing about, and really like that you noticed that. And what was the other thing? Like you mentioned, the time of, traveling to the rides as an explicit activity as well, kind of taking into account that time. And really, I thought that was really interesting as well, with the expected duration in park as being an attribute. That's a really nice idea, actually. So kind of modeling part of how, when will people exit the system based on how long you might expect people to want to spend in the park. So yeah, excellent. Thank you very much. So that was Pokey. RJ McCall, would you like to present? There is no pressure to. If I hear silence, then I will move on to Sid, but if you'd like to present, then you are welcome to.
Hi, Sammy. thanks for the offer. I think we'll pass on this one, but we did have a really good time looking at the complexities of a restaurant, queuing at a restaurant, and we kind of thought about how we could reduce the waiting time if we had, like, specialized staff or a simplified menu. So it was a really good discussion we had, but pass on presenting. Thank you.
Fantastic, no problem at all. Yeah, I really liked what I saw when I popped into your room a few times. So yeah, no, that's all good. Thank you very much. Sid, we will go on to then. I can see a screen, but I cannot hear a person.
Yeah.
Oh, there we go.
Everyone can see my screen. So we decided to go with the hypothetical of Pizza Hut, but rather than a Pizza Hut restaurant, Pizza Hut takeaway delivery service. So the sort of starting point for us was the Pizza Hut approaching us, saying that they're losing customers due to the time taken to deliver their pizzas and to serve their customers. And the what if questions that they had were, what if we've got new ovens? What if we've got some more kitchen staff? What if we hired more delivery drivers? What might happen if we suddenly start to get a big influx of orders? And what if we put another phone line in? So we drew out this model. So we've got two generator points. So either people walking in to order over the counter, or people telephoning in to make orders over the phone. So our order taken is the first activity, and the resources associated with that would be the front of house staff taking the orders, the separate staff taking orders over the phone, and the phone lines themselves. So then there will be another queuing point where the order gets sent through the kitchen, at which point the kitchen staff then have to review that order to see what's required. It then branches off into three separate potential activities, either the preparation of sides, preparation of pizza, or the preparation of the drinks. I guess you could sort of start to build in different priorities around that then. I guess maybe more simple orders, or if a customer was just ordering drinks, you might have those orders prioritized to get the quick ones out of the way. It then goes into, if it's a pizza, it needs to go into the oven. And if it's a side, there's a question over, is it cooked or not? If it is cooked, then it also goes into the oven. So then it introduces another resource, which is the ovens themselves, which relates back to the what if questions. The next stage is that the orders all have to be combined. So then it goes back out to the front of house staff. So that's back onto the resources of the front of house to combine those orders. And then it passes through to, if it was a walk-in, it's just delivered straight to the customer. And then that's the sync point. The customer gets the pizza order and leaves. Alternatively, if it's a delivery order, then it has to go to the driver, which forms another queue point. Based on whether or not there's any drivers available or they've returned from the previous delivery. And then the next point is that it obviously gets delivered to the customer for the final sync point there. So yeah, that was our sort of model where we got to.
Excellent, thank you very much. I'm liking your what if questions, and also I think there's a nice neat model. You managed to get a lot clearly shown on one page there. Also really like the idea of the priority for the different orders, and I sort of get the impression that would actually be a really useful thing for some real life restaurants ever since things like Uber Eats and Deliveroo got introduced. So I think they could learn a lot from a model like this potentially to make sure everyone gets a good experience. So thank you very much. Who are we on to now? TIA.
Yeah, that's us. I think, Chris, can you share the screen, would you? Great. Chris and I are going to tag team this a little bit. So can you hear me all right?
Yeah, that's coming through. Thank you.
Cool. So our scenario was a bit different. It was a rehoming centre for cats, because we know Daniel's not a cat. So the generator here, well, initially the entities themselves are the cats that are being submitted to the centre. So they come in the red box on top left there. They are triaged when they arrive, and some unfortunately are not well enough to go further and are put to sleep by the vet. Some need treatment in which case they are put into one of the treatment cages. And this has an associated time with it, based on some kind of a distribution. Or if they're healthy when they come in, they go into the main rehoming area. And we've got a certain number of those, and that's our main capacity constraint, if you like. From there, they can obviously become ill and then go back around that sort of treatment loop. Alternatively, they sometimes need some kind of behavioral rehabilitation before they can be safely rehomed. So again, we've got another set of areas, if you like, in the rehoming centre where the staff will work with them for a certain number of days, roughly 2 months on average, something like that. And then they can be put back into the rehoming area once they have been successfully rehabilitated. From there, some will just become ill and need to be put down for whatever reasons. A lot will be rehomed. And we can go back up through the treatment loop at any point because, you know, cats can get sick at any point. So the what if questions that we were going to ask with this model, the main one is, what if we had more treatment cages? At the minute we've got 2, but they're a real bottleneck. So the outcomes we would look at is, when would we reach the maximum occupancy of the whole system? And this is why we needed to look at all of these different parts, not just the treatment cage element, which if we were going to simplify down would be the bit we'd have zoomed in on. But because we want to know of occupancy of the whole centre, then we need to have a look at all of these different things in the same time. Another outcome we could look at was, how long would cats stay in the system if we had an extra treatment cage as well? So we've Chris has color coded this for us such that, and in the top right we've got the little key here. So red's the generator, the orange triangles are the activities we've got. So that's triage, rehoming, treatment cages, behavioral rehab. The grey boxes beside those are the resources associated with them, and the green bits below are the average times for each activity, and they'll be based on different distributions, as we said. And then the blue bits are the sinks, and the sinks, they can leave either because they've been rehomed or they've been put to sleep. Cats do go in sinks a lot. We have a cat in a sink at the bottom, so for no other reason than there's lots of pictures on the internet of cats in sinks. I think that was all of ours. Yeah, we've got those cues, we've got the resources, and we've got the what if question. Yeah, I'll stop there.
Fantastic. Thank you very much. And I think I came into your group when there was a discussion about how no one is ever going to forget what a sink is now, because, or what the name of that is, because, you know, we will all just remember the cat, which is, yeah, fantastic. Really liked the discussion of kind of like the boundaries of your model and what was necessary to include and why. I thought that was a really well recognized. And I really like that you'd kind of thought about your branching paths and the way that things could loop round and getting the percentages in there as well. And as Dan says, excellent what if questions, and he may pinch the cat in the sink for next year's slides. So thank you very much. Zylog, I'm aware that we've not got long before lunch, but let's just make sure we get through you guys, and then we will all go and take a break after that. So have we got someone from Zylog?
We do. I think that Sean might come in as well. Just going to click share. Okay, so we are also kind of a bit basic, but and picked a theme park. Our image generation was kind of fun in terms of the way it did text, but interesting. So we actually thought of like doing an entire theme park or a fun fair, but we thought that was actually a bit broad because there was too many, like I say, that Dan was saying about using governor models. So we decided to actually go into one ride, and then that could be built into a larger model in the future if we had to, rather than trying to model the entire park, because that was much too much of a complex system. So that was our first kind of breakdown. And then so we looked at the what if questions about this and kind of mapped out what we thought the system of the ride was like. So we have people entering the ride, queuing, they had a fast track queue, height check, and then kind of like what properties each of them had. So we mapped out the system first. You get out, ride the roller coaster, get out of your cart, staff clean the cart, and then some people get a photo at the end. But from that, so that we did that initial thing, and then we sort of mapped out it as the more of the DES system. So again, we have this people arriving at the ride, which is our generator, and they can either be like arriving at fast track or regular, because that's from the ticket office. So the yellow comments here are where we think the data might come from. So then you can queue for your height check, and you can get bored of the queue, which might mean you go back and go get a fast track ticket, or you get scared because the ride looks too fast and scary. Because one of the questions is, well, what if we increase the speed of the ride? Will that get better? But that'll increase will probably increase the chance of reneging, because people are scared, and also increase the cleanup time and the amount of maintenance it needs. So maybe that might not help. You get your height check. One of the questions is, well, if we could save staff and have an automated height check, would that speed up people going through the system and get people more going through? You get into a cart. One of the questions we had is about whether actually we needed to model carts separately or just roller coaster seats. So we just actually decided that in fact the resource we're using here is roller coaster seats. And so when the entire ride goes into maintenance, which means it's not operational, the roller coaster seats all go to this kind of unconnected activity. So I don't know whether that's a thing that you have like these unconnected ones, because this is the primary pathway for people. But this staff go in their staff break, engineer goes into engineer break, and the roller coaster goes into maintenance. That aren't connected to this main pathway which people go through, because that's where they go. Yeah, people ride the roller coaster. People then get out of the cart. We was wondering again, getting out of the cart, we might be able to speed that up if we had more exit count doors, but that might not be the same, because maybe that, again, a what if question was whether having more doors out would speed up, or just we need more staff to get them out, or whether it's just a slow people getting out. Again, then queuing for photos is like a little separate queue, and again we can sync whether either they leave the ride or they get a photo. So that's a really quick look at that. Do you have anything to add, Sean, that I missed out? Because I was trying to go very fast.
No, I think you've got everything.
Yeah. Oh yeah, we did have a little look about looking at, again, these objects of people and staff as well. Cool. There we go.
Fantastic. Thank you very much. And Dan, I must say, has said in the chat, this place looks amazing. Do love your your little intro there. And I think this is a really nice thing to end on, actually, because it's so good to see the level that you can model the same thing at, and actually depending on what your what if questions are, that actually both kinds of modeling can be valid. And that's such a nice contrast to the sort of very high level modeling, and actually really shows how some of this class-based stuff that we've been looking at can get really powerful as well. So you can have a class with this level of detail and actually then put that into a larger model of a whole theme park and replicate it without having to do all that work again and again. So really nice one to end on. Thank you very much. I'm going to deliberate over lunch on where I'm going to put those PSG points, because it has not been an easy decision. I've got reams of notes to look back through. So thank you, everyone. I think that's been some really nice models, and I hope that's really helped everyone kind of see the different ways that you can conceptualize all this stuff. Dan, anything to say before we head off to lunch?
No, just say, yeah, I totally agree. I thought they were really, really nice. All of them very creative. A lot of theme park ones, but even all of those were really different. You'd looked at really different aspects of it, and it just really nicely demonstrated to me, what a creative thing this is, and the importance of creativity when you're trying to tackle very similar problems. In some cases, you had almost identical what-if questions, but choosing to look at it in very different ways. So yeah, really hammered home for that. But yeah, really, really nice. Really interesting designs, I think. So let's. I'll let Sammy deliberate over lunch. So we've gone 5 minutes over. Let's. If people are happy, we'll stick with 1:30. So we have 55 minutes. The bit I was going to do on generator functions, I can whittle through quite quickly. We've also got a bit of a buffer at the end of today, which we won't need all that time. So we should be able to make up the time. I'll go through generator functions very briefly after lunch, after Sammy's given us her judgment. And then we'll get straight into this afternoon talking about how we do all this using SimPy. Brilliant. Cheers, everyone. See you at 1:30.